Okay, in this video, we're going to prove a basic fact of the ordering of integers, namely that if a, b, and c are integers, and a is less than b, then a plus c is less than b plus c. Now, in order to do this, we have to prove it according to the definition of ordering, namely that a less than b means that b plus negative a is in the natural numbers. So this is what we start with. This is our start of the maze. And what we want at the end is a plus c less than b plus c. And what that means, according to the definition, is that b plus c plus negative a plus c is in the natural numbers. So this is our end state. By the way, WTS stands for want to show. So we start here, b plus negative a in the natural numbers, and we want to end here. B plus c plus negative a plus c is in the natural numbers. So intuitively this makes sense because here we have c added, and here we have c subtracted because it's in the is in the negative sign. So we can tell that in this proof, at some point we're going to add c as well as the additive inverse of c. And then we're just going to manipulate the order of the terms in order to get it in this form. So let's start off with the beginning. We have b plus negative a in the natural numbers. And this is true according to the definition of less than and our assumption that a is less than b. So next, we do the setup to get c plus negative c into this expression. We know that b plus negative a is equal to 0 plus b plus negative a. And this is true according to the property of additive identity. And we know that 0 is equal to negative c plus c. And this is true by additive inverse. Okay, so we have all our terms in. Now what we need to do is a rather tedious process of rearranging terms. So the first thing we're going to do is we'll reverse the order of c and negative c, since we want the c on the left side and the negative c on the right side. So next, we will get the b grouped together with the c plus negative c, because our goal ultimately is to move the b all the way over to the left. So we group the parentheses like so by the property of additive associativity. Next, we do, as we said, we move the b all the way over to the left, and we can do this by additive commutativity. Next thing we do is we want to group the c together with the b, and we want to do this because our expression here, the form has b plus c in parentheses together on the left. So we have b plus c in parentheses plus negative c, all of which in parentheses plus negative a. And we did this transformation by associativity. Next, we will group negative c together with negative a by associativity, again, because we want these two terms together on the right. Then we flip the negative a and the negative c by additive commutativity, because we want the a to the left of the c. So now we have b plus c plus negative a plus c. Negative a plus negative c. And all we have left to do is show that negative a plus negative c is equal to negative a plus c. And the easiest way to do that from our standpoint is to use the property that we proved earlier, that negative 1 times x is equal to negative x. So we'll do that twice here. Negative a plus negative c is equal to negative 1 times a plus negative 1 times c. And the justification is the fact that we proved earlier. Now we can use distributivity to pull out the negative 1. So negative 1 times a plus negative 1 times c is equal to negative 1 times a plus c. And that's by distributivity. Finally, we use the same property that we proved earlier to see that negative 1 times a plus c is equal to negative a plus c. Okay, so the conclusion to all of this is that b plus negative a is equal to b plus c plus negative a plus c. So b plus negative a is equal to b plus c plus negative a plus c, but it's also in the natural numbers by our assumption. Therefore, a plus c is less than b plus c by the definition of less than. So notice how every single step here was justified by one of the axioms or properties that we previously proved. And this is sort of the character of axiomatic proofs. You're manipulating strings of symbols according to specific rigid rules. This is the sort of mindset that you want to have going into such axiomatic proofs.